Hello everyone, it's Ampersand. In this video we'll delve into the features of a unique Linux distribution NixOS, and of course take an in-depth look at the Nix functional package manager and its features. I'll explain how to use Flakes, Home Manager, Disco and much more. Let's go! In 2003, developer Elko Dolstra created the declarative package manager Nix as part of his PhD thesis to address the shortcomings of traditional imperative package managers. It's called declarative because it adheres to the declarative programming paradigm, which focuses on what needs to be done rather than how to do it. If we draw an analogy with natural languages, you can look at it as imperative mode and declarative mode. Thus, in traditional package managers, installing a package involves writing various commands, that is, commanding. In the declarative Nix package manager, however, installing packages involves editing a script, which is essentially narrating. But why does Nix use a declarative approach? Let's delve into it. Software deployment is the process of distributing a program from one computer to another in a way that it works after being distributed. Sounds simple, we just need to copy files from one place to another, but it's a bit more complex. Let's imagine a developer built a program and tested it in various use cases to ensure it works correctly. The problem is that the system on the end-user computer may differ from the developer's system. Programs rely on so-called libraries. Subprograms use it to facilitate development. For example, the video editor Kdenlive uses the Qt library to render its interface. And if the library necessary for the certain program to work is missing on the end-user system, the program simply won't run. In other words, having the same input data, the same program, we get different output results. It works there, but doesn't work here. Another problem with software deployment is interference. Updating one package may require updating the library it depends on. At the same time, another package that also depends on this library may turn out to be incompatible with the new version. Thus, updating one package may break another that is completely unrelated to it. This problem is called interference. Now let's take a look at how the Nix package manager solves all these problems. It isolates each package in a directory whose name contains a cryptographic hash containing all the input data used during the package deployment, including dependencies. Thus, package files are not scattered throughout the file system as in traditional package managers, but neatly arranged in the nix/store directory. Moreover, the dependencies themselves are also isolated. Thus, even if the necessary library is installed on the system, but is not specified as a dependency for the developed program, it will not be able to run. Therefore, the Nix package manager is called deterministic. With the same input data, it yields the same result, regardless of the environment. If it works here, it works everywhere. If it doesn't work here, it will not work anywhere. In addition, isolation allows having two versions of the same package on one system, which is very problematic to implement using traditional package managers. This solves the interference problem, because you can have two separate isolated versions of a library for different packages. The script for installing all packages is usually called default.nix and represents a function that takes dependencies as an argument and installs the program according to the provided instructions. Nix combines both the declarative and functional paradigms, and packages here are represented as functions. One of the main properties of functional programming is the determinism of functions. A function should produce the same result for the same set of arguments and not affect the external environment, that is, do not have side effects. That's why the declarative functional approach works so successfully in the software deployment sphere. Functions that build packages are called derivations, as they derive from the input data of a component. Packages are immutable. After installation, they never change. When upgrading the system, a new directory for the package is created, while the old one remains. Whereas traditional package managers replace files of the old package version with the files of the new one. Another feature of updates in Nix is that they are atomic. During updates on traditional package managers, there is a time window where one part of the system has been updated, but the other has not. If the update is interrupted at this moment, the system may break. Whereas with Nix, because the old packages remain present, there is no such time window. The system either updated or not. There is nothing in between. Later on we'll discuss how exactly this works. Since Nix highly values backward compatibility, before installing a package, the default.nix file is translated to a more primitive language, somewhat resembling JSON. This file is called a store derivation. After translation, the package is installed according to the instructions from this file. This is done because the Nix language is constantly changing to accommodate new features. This means that we would have to be able to deal with the variability in the Nix expression language itself. Several versions of the language would need to be able to coexist in the store. Translating default.nix to a more primitive language solves this problem. This is analogous to the way that compilers generally do the bulk of their work on simpler intermediate representations of the code being compiled, rather than on a full-blown language with all its complexities. The contents of the store derivation are all the input data required to build the program. Cryptographic hash of the derivation is created from the contents of this file, which is then placed here as the value of the output field. First, the file is hashed using SHA-256, resulting in a 256-bit hash consisting of 52 characters. Since this is too long for some file systems, Nix truncates the resulting hash to 160 bits, resulting in a length of 32 characters. The Nix package manager retrieves packages from the Nix packages repository, which is the largest software repository at the moment. It is divided into several so-called channels, that is, branches with different versions of packages. This can lead to some reproducibility issues, as different machines may use different channels, or the same channel but different commits. This problem is addressed using Flakes, which I'll explain in the practical part of this video. Essentially, Nix operates with packages similarly to how low-level languages like C and C++ work with memory. Instead of RAM, we have disk storage. Instead of objects and their values, we have components, meaning derivations. Instead of addresses, we have paths to derivations. Instead of dereferencing pointers, we access derivations through their paths. Instead of pointer arithmetic, we perform operations on strings representing derivation paths. Instead of dangling pointers, we have paths to non-existing derivations. Instead of a directory tree, we have a dependency tree, and so on. Here we can draw an analogy that languages lacking built-in pointer discipline, like assembly language, represent all traditional package managers. Package files are disorganized and scattered throughout the file system. Both working with traditional package managers and assembly language rely on assumptions. Assumptions such as the path to a specific file being a reference to the required library, or that if an array starts at this memory address, then the 100th element of the array is at that address. In both cases, if your assumption is correct, things go smoothly. But it could all be simpler if we relied less on hope that our assumptions are correct, and more on certainty. That's why low-level languages like C and C++, with enough pointer discipline to support conservative garbage collection, were developed, as well as by the Nix package manager, where all packages are isolated in separate directories. Meanwhile, high-level languages with modern garbage collectors represent a yet-to-exist software deployment system that theoretically will surpass all existing ones. All this time we've been talking only about the Nix package manager, which can be installed on any distribution, and even on macOS. In the early days of Nix, it was unclear whether a full-fledged distribution could be built on its basis. To test this, work on NixOS began shortly after the development of Nix. Elka Dolstra pointed out that modern methods of configuring operating systems, much like software deployment, are very chaotic and undisciplined. Configuration files, like packages, are scattered throughout the file system. They can be seen as imperative data structures. They are updated in place by system administrators' actions, making the system non-deterministic and creating difficulties for reproducibility. In contrast, the NixOS distribution offers a declarative approach. The entire system configuration is described as pure functions in the Nix functional language. Thus, with the same input data, we get the same system, making it reproducible. NixOS lacks bin, user, or lib directories, and etc mainly consists of symlinks. Everything is isolated in the nix/store directory. The determinism of NixOS and isolation of all packages makes it easy to implement system rollbacks to previous configurations. Thus, NixOS allows for a fully deterministic system with rollbacks and reproducibility, making it a really attractive choice for system administrators. Now we're moving on to the practical part of this video, where I'll talk about installing this distro and how to use it, because the experience of using NixOS differs significantly from other distributions. On the official website, there are ISO images with and without graphical interface. I'll download ISO without a graphical interface. In this case, the installation process is similar to installing Arch Linux, but with NixOS it's much simpler. In the graphical ISOs, there is a Clamaris installer, which also works. At the very beginning, I created two partitions, boot and root, formatted them in FAT32 and ext4 respectively, and mounted the root partition to mount. Next, you need to execute the command NixOS generate config --root mount to generate the configuration. Opening it, you can see a huge amount of commented options, which we'll talk about a little bit later. And since we'll have to write a lot of configurations to set up NixOS, welcome to the brief course on the Nix functional language. In Nix, there are the following data types: strings, numbers, boolean values, and paths. There are arrays, which are called lists, and elements here are separated by spaces or new lines. There are objects, which are called sets, and accessing the value of an object property is done through the dot operator. All properties are separated by semicolons, which are mandatory in Nix. Never forget about them. To create variables, the let and int syntax is used. For example, this piece of code will create a set containing 3 variables. To run code from a file, the nix instantiate --eval command is used. Using the dot, we can get the specific value of each variable in the set. The with keyword allows you to use the properties of specified objects as list values. To create functions, the following syntax is used. For example, this function will square the specified number. A function can accept set as an argument. For example, this function calculates the perimeter of a rectangle with sides a and b. 3-dot syntax allows function to accept an unlimited number of arguments, but to access them, we first need to create a set args containing all function's arguments and specify b as an element of the args set. Congratulations, now you know the Nix programming language. Now let's come back to our configuration.nix file. It is a function that takes arguments like config, packages, lib, and others, and output the modified configuration of our system. Now let's uncomment the lines with hostname, network manager, and time zone. Don't forget to correct them to your preferences. In the future you'll have to edit this file a lot, but for now, that's enough. Then we need to execute the command NixOS install. This will install the system in mount, according to the configuration we wrote. This process will take approximately 15 minutes. After that we reboot and ready to go. While all this is great, disk partitioning during the installation of NixOS is an imperative process, not declarative. Therefore, I'll show an alternative installation method using the disco utility, which allows you to declaratively configure the disk, greatly simplifying the reproducibility of the system. For demonstration purposes, I'll show this on the NixOS ISO with KDE. Let's open the terminal and browser, find the disk repository in GitHub, create a disco.nix file, and copy this code from the repository. Here we're creating a new GPT partition table with a boot partition of 500 MB formatted in FAT32 and a root partition formatted in ext4, which will take up the remaining space. First, I'll slightly reduce the size of the boot partition, create an 8 GB swap partition, and change the root file system to Btrfs. Since I'm doing this on a virtual machine, I'll have to replace dev.sda with dev.vda, but you don't have to do this on a real hardware. That's it, our disk configuration is ready. If you want to customize it further, I'll leave a link to the Disco documentation in the description. There are templates with partition tables for Btrfs subvolumes, LUKS encryption, LVM, root on ZFS, and much more. Now let's save our file and enter this command from the repository's readme, specifying the path to our disk.nix configuration. When it finishes, all partitions are automatically mounted in mount, and all we have to do is run NixOS generate config --root mount and NixOS install. Thus, if you need to install the same NixOS on multiple computers, you just need to copy disco.nix and configuration.nix to them and run 2 commands, and you'll get absolutely identical systems with the same disk layout. But let's get back to the system we installed last time. Since we'll be editing the configuration a lot, it would be nice to install a text editor, like Vim. As I mentioned before, programs in NixOS are installed not through commands, but through a configuration file. So we open the configuration via nano, find these lines and uncomment them. If you need to install more programs, just add them to this array, separating them with new lines without semicolons. To find out the name of a specific package, you can visit the Nix package search webpage. You could of course find it using the command nix search nix packages, but it will take quite a bit of time and memory because it indexes the entire Nix packages, which is the largest package repository at the moment. After adding the necessary packages, save the file, and to update the configuration, we write NixOS rebuild switch. This command will update our system according to the new configuration. And now we can use Vim. If we reboot now, we'll see that there are two NixOS configurations in the bootloader. The second one appeared after we installed Vim, and if we boot up the first one, Vim will not be there. New options in the bootloader are generated every time we run the NixOS rebuild switch command. When booting into old configurations, old packages are not removed, only symlinks are changed. There is also the command NixOS rebuild boot, which will also update the system, but we'll only see the updates after rebooting and choosing any option in the bootloader. NixOS rebuild test will update the system, but won't add any option in the bootloader. But what exactly happens when we run the NixOS rebuild switch command? Essentially, it is a bash script. Its working process can be divided into 5 parts. First, using the nix build command, the configuration.nix file is revised. Necessary changes are detected, and packages that need to be installed are determined. Then the same command downloads and builds all the necessary packages. As a result, a new system profile is created, which is stored in this directory. It contains bootloader settings, all files from the etc directory, kernel settings, and much more. Then the profile we created is added to the bootloader, and new symlinks are created from the nix/store to etc and other parts of the system. And the last final stage is restarting systemd services. This process essentially allows you to create a new system every time you run this command, and in most cases you won't even need to reboot to see the changes. But let's get back to configuring our system. Now we need to create a user account. To do this, we write user@am_username, set a password for it, open the config, uncomment the lines responsible for user configuration, and slightly edit them. Save and update the configuration. Now we can exit from root and log in as a regular user. Next, let's install a desktop environment. The NixOS wiki has instructions for installing any desktop environment or window manager, but in this video I'll install XFCE. In the configuration file for the Xserver object, we change the enable property to true. For the desktop manager object, we enable XFCE and set display manager.default session to XFCE as well. Don't forget about the semicolons. Again, update the configuration, and after rebooting, we can now use XFCE. The NixOS rebuild switch command does not update package versions. To do this, we need to update the channel first. By running the nix channel list command, which must be executed as a root, you can see that we have channel 23.11. If you need the latest package versions, you can replace the current stable channel with the NixOS unstable using these two commands. You can also replace individual packages with unstable versions by adding unstable to the package name. But if you just need to upgrade packages on your system, write the commands nixchannel update and NixOS rebuild switch upgrade. As I mentioned in the theoretical part of the video, packages don't get replaced during an update. The old versions are still present in the nix/store, and as you can see, we've accumulated 5 generations of NixOS, and if needed, we can roll back to the very first one. However, I'm going to delete all generations except for the current one, to free up the disk space. This can be done with the command nix collect garbage-d. System cleanup can be automated. By adding the following lines to the configuration.nix, generations older than 30 days will be automatically deleted every week. Another interesting feature of NixOS is Home Manager, which allows you to declaratively configure the user environment. To use it, we need to add the corresponding channel, either the current release or unstable. You can find these long commands in the description. Then we need to specify it in the list of packages and install it. As an alternative, you can use Home Manager as a module inside the configuration.nix without installing it separately. The downside of this approach is that updating the Home Manager configuration will require root privileges. Now let's create a file .config/nixpackages/home.nix and write a simple configuration. First, we must specify the username, home directory path, and version, even if you're using the unstable channel. Now, to see if it works, let's add a new alias. We update our configuration with the Home Manager switch command, restart the terminal, and as you can see, everything works. Also in Home Manager, you can specify individual packages that will be available only for the current user. For example, by running this configuration, the current user will have NeoFetch and HTOP installed. Now let's configure NeoVim and its plugins through Home Manager. Add the following lines to your home.nix. After updating the Home Manager configuration, we'll be able to use NeoVim with the NerdTree plugin. Additional plugins can be found on the Nix Packages search webpage. With the same approach, you can configure Git, various window managers, Waybar, Alacrity, and much more through the Home Manager. I'll leave the full list of Home Manager options in the description. Attentive viewers might have noticed that updating channels on NixOS is imperative, not declarative, which can cause reproducibility issues. After all, the configuration can be the same, but the channels can be different. And here comes another feature of NixOS to rescue: Flakes. Essentially, Flakes allow you to write code in the Nix language whose dependencies are version pinned in a log file. The contents of a flake can be roughly divided into two parts: inputs and outputs. Inputs are the dependencies of the flake. Dependencies can be packages, channels, or other flakes. Outputs is a function that takes inputs as arguments and returns packages, shells, or even system configurations. After executing the code from a Nix flake, a flake.log file is created, where the versions of the dependencies we used are hashed, solving the reproducibility problem. The flake feature may seem really complicated for many beginners, and from experience I can say that the best way to understand how they work is to try them out yourself. So let's write our own flake, which takes the Nix packages channel as an input and outputs our configuration. To start, we need to enable Flakes, since it's an experimental feature. You can do this by adding this line to configuration.nix. Using Flakes allows us to store configuration files anywhere, not necessarily in etc/nixos. So let's create a Nix folder in the home directory and move the contents of etc/nixos into it. Next, create a file flake.nix. Open curly braces and write the flake's description. Now let's create our inputs and outputs. As an input, specify the Nix packages along with the URL. Here you need to write the Nix packages channel you want to use, for example 23.11 or 24.05. Or if you need the unstable branch, write NixOS unstable here. For outputs, we'll define a function that takes the Nix packages channel as an argument. Then we write NixOS configurations, and the hostname we specified in configuration.nix. Here configurations is plural, because we can create multiple configurations for different computers with different hostnames. Then write =nixpackages.lib.nixos system. Open curly braces again and specify the architecture of our system. In my case, and probably yours too, it's x86_64-Linux. Now define the modules that our function will output. For now there is only one module, our configuration.nix file. To recap, the outputs function, which takes the specified Nix packages channel as an argument, creates a configuration for a system with hostname NixOS and 64-bit architecture, as well as one module, configuration.nix. Save it, exit, and run the command to update the flake. It's the usual NixOS-rebuild switch with the --flake flag and the path to the flake. You can use the hash sign to specify an alternative hostname if you want to update the configuration on another computer, but in this case it's not necessary, since we only have one configuration. Now wait for the channel to update along with the configuration. After that we can open the generated flake.log file, where the current commit of the Nix packages 23.11 channel is hashed. Thus, this file will help us to reproduce our system identically. You can update the flake.log file using the command nix_flake_update. So, we have a flake that builds the configuration of our system, but we forgot about the Home Manager. Let's fix that. Open the flake.nix file again and add a new attribute in the input section called Home Manager. If you're using the unstable branch, you can leave this link as it is. But if not, specify the exact release with the channel you're using. Just make sure that the Nix packages and Home Manager channels match. To ensure that a specific version of both Nix packages and Home Manager channels are fully synchronized, we need to write this line. Now add the Home Manager argument to the outputs function and create the Home Manager configuration, specifying your username. Then create the packages attribute, which is needed for Home Manager to install packages, and the home.nix module. It probably drives you crazy to see the system architecture written twice here, so I'll fix that using the let's in syntax I mentioned in the brief introduction to the Nix programming language. Instead of creating the system attribute, we now write inherit system and replace this line with the $, followed by curly braces and the system variable. Save the changes and copy our home.nix to the flake folder. Update the system configuration, and now we can update the Home Manager using the command Home Manager switch flake and path to the flake. Here you can use a hash sign to specify the username whose configuration you want to update, but since we're updating our own, it's not necessary. The next step is to conventionally split our configuration into modules. I'll demonstrate this using Home Manager as an example, but the process is the same for creating modules in the main configuration.nix file. I have some code for configuring bash, and I'd like it to be in a separate file. To do this, I'll create a file called bash.nix in the same directory as our configs. Open curly braces and paste the bash code, removing it from the original configuration. Instead, write here imports, which is an array containing the path to the bash.nix module. Save it, update it, and everything works. Now exit the virtual machine and I'll show you my NixOS configuration. My Flake.nix is not much different from what I wrote in the virtual machine, but here I use the unstable branch and I have a channel with old packages, in case the fresh ones fail to work. I also use NixVim here, which is a distribution of NeoVim that can be fully configured using the Nix expressions. If you'd like to see the full NixVim guide, let me know in the comments. All configuration files are split into two folders, NixOS and Home Manager, where each small element like Qt or environment variables has its own separate module. They're all imported together in the bundle.nix file, which is then imported in the configuration.nix or home.nix. Unnecessary modules can be disabled using the disabled modules list. If you're new to NixOS, you'll find a lot of useful stuff in my configuration, so feel free to explore, copy, and use it to your heart's content. Now let's summarize. Here are the pros and cons of NixOS. First of all, reproducibility is paramount. Once I had to migrate NixOS from hard drive to SSD. All I had to do was create a simple disco.nix, copy the configuration, rebuild it, and I got an identical system with the same package versions thanks to the flake.log. Control of the system achieved through declarativeness is another big advantage. In other distributions, package files are scattered throughout the whole file system, but in NixOS, everything is neatly organized in Nix-list store. Rollbacks to previous configurations can also be very useful, especially for unlucky experimenters like me. The system's resilience is worth noting. You can install and uninstall any packages, change environments multiple times, and the system won't flinch. And the last but not least, the huge number of packages available in Nix packages repository exceeds even the legendary AUR. However, some of the advantages of NixOS may turn into disadvantages. For example, installing packages takes significantly more time and disk space compared to other distributions, because Nix needs to evaluate all derivations, translate them, download, build, update other parts of the system according to the new configuration, and much more. This steep learning curve is another drawback, although it's mainly challenging in the beginning. During the first few weeks of active usage, you might find yourself tearing your hair out, but it gets easier over time. One of the reasons for the complexity of Nix is the lack of detailed documentation. There are many resources for learning NixOS, but not all of them cover topics in detail, which can lead to many why, where, and how exactly questions. So, as parting words, I'd like to recommend some resources for further learning of NixOS. Links to all of them will be in the description. Firstly, the NixOS manual covers instructions for various use cases, including installation, configuration of individual packages, file systems, and much more. For learning commands, Nix syntax, and related topics, I recommend the Nix reference manual. NixBuilds offers short guides on using the Nix package manager, including creating packages, tips, and tricks. Home Manager Option Search is a vast resource for finding options for configuring your user environment. Zero to Nix provides guides and tutorials on everything related to NixOS, from the Nix language to system configuration. And for a deep dive into Nix with detailed explanations of every aspect, I recommend reading the NixOS developer Elke Dolstra's PhD thesis, which covers everything as detailed as possible. Lastly, google.com is your friend. Seriously, some things can be found on Google in 10 seconds, whether it's downgrading a package, changing a kernel, or installing Word Manager. Many issues are often solved after visiting the first link in your search engine. NixOS is much bigger than it might seem at the first glance, and in this video we've only covered the tip of the iceberg. So my advice is to try, explore, and learn. Only through your own personal experience you can truly understand NixOS. Well, that's it for today. Thank you so much for watching this video. Don't forget to like, subscribe, leave a comment if I helped you, and have a great rest of your day.